Welcome. This is Coach Dorf. We're going to continue our discussion about calculus. Today, we're going to talk about optimization problems. Our goal is to use the second derivative test to find the maximum or minimum values for a word problem. Now, as a review, what is the second derivative test? Well, we have a function, we take its derivative, we set it equal to 0, and we solve that, and that gives us our critical numbers. So we find the critical numbers of a function. And if x equals c is one of those critical numbers, then we take the second derivative of the function and we evaluate it at c. If the second derivative is positive, then there's a minimum at c. If the second derivative is negative, there's a maximum at c. Now, in solving these optimization problems, we'll use the second derivative test, but I've outlined the steps that I would say I use to solve these problems. All right, so it's a a step-by-step approach. All right, so the first thing I would do is after I read the problem is to define the variables and write an equation using the information given in the statement of the problem. Then I write down what I want to maximize or minimize. And then I use that to write a function with only one variable. All right, then we take that one function and we apply the second derivative test to it. All right, we find the critical numbers, and then we evaluate those critical numbers at the second derivative, and then we can determine whether there's a max or min, and then we answer the original problem. So those are the steps that I use in solving an optimization problem. Let's look at a specific example. Find the dimensions of a rectangle with area 100 square meters, whose perimeter is as small as possible. Now, if we kind of sketch out some examples here, here's my rectangle. I could have side length of 50 and width of 2. So then the area would equal 50 times 2, which is 100. And what would the perimeter be? Well, the perimeter is the area all the way around. So we have 50 on one side, and then we have 2 on the right side. On the top, we're going to have another 50. And on the left side, we'll have 2. So if we add those all together, we get 104. We could draw a different rectangle, and suppose this one had the length of 25 and the width of 4. So the area would be 25 times 4. So we still have 100. And the perimeter here would be 25 plus 4, and then another 25 plus 25. And then another 4 plus 4, and that would give us 58. Well, that's better than the previous one we did, but how do we know if we've got the exact answer to this, that it's the smallest as possible? Well, to do this, we're going to use math, and we're going to draw a general rectangle, and we're going to call the bottom side L and the right side W, where L is going to equal the length of the rectangle, and W is equal to the width. All right, this is now where I'm starting part 1 of solving this problem. I've defined my variables, L and W, and I'm given an equation in the problem. I'm told that the area equals 100. So area, which is L times W, equals 100. Oops, let me redo that. There, that's supposed to be 100. There, okay, so this is the pertinent information we have right now. L and W are defined, and I've got the area is L times W equals 100. All right, then in part 2, what do we want to minimize or maximize? We want to minimize or make as small as possible the perimeter. We'll call that P, and the perimeter is what? Well, it's adding up all the sides around. So if I go to my diagram and I put my other sides in there, I'm going to get L plus W plus L plus W, which would be 2L plus 2W. All right, so we got this P, which is 2L plus 2W. And again, I'm going to circle that in red because that's important information there. That's what I want to minimize. Well, part 3 then says we want to take what we have so far, and we want to write one function. We want to write a function in one variable. Right now, we have a function P in 2 variables. It has L and W in there. it's much easier in taking the derivatives and solving this problem if we get rid of one of those variables. And we can do that by using the formula for the area up there, that L times W equals 100. So right now we know that L times W is 100. I can solve for one of the variables. So let's just solve for W. So I can do that by dividing both sides by 100. And now we're going to take that and we're going to substitute that into the P equation for the perimeter. So we're going to take W equaling 100 over L and put that in here for W. And when I do that, then I get P equals 2L plus 2 times 100 over L, which I can then write as 2L plus 200 over L. So I'm going to write that now as my function in terms of the variable L. P of L is going to equal 2L plus 200 over L. Now I know I'm going to be taking the derivative in the next step, so it's going to be easier if I rewrite that last term as L to a power. So I'm going to write this as 2L, and then instead of putting it 200 over L, I'm going to have 200 L to the -1 power. And that's how I'm going to write my P there. Okay, so now we have a function in one variable, and the next step is we use the second derivative test. So I'll take my function, P of L, which is 2L plus 200 L to the -1, and I take the derivative of it. So derivative of 2L would be 2. Derivative of 200 L to the -1, I'm going to get 200. I bring the exponent out front by the power rule, so it's a -1. Then I have L. I subtract 1 from the exponent in L. Right now it's a -1, so -1 minus 1 would be -2. And I could rewrite this then as 2 minus 200 L to the -2. But to help solve that, I'm going to also rewrite it as 2 minus 200 over L squared. And because we want to do the second derivative test, we want to find the critical numbers. So that means we want to find the derivative of the function equal to 0. So we're going to set that equal to 0. Now, to solve this, I'm going to bring over the 200L to the right side of the equation, and that will give me 2 equals 200 over L squared. I can multiply both sides by L squared, and I get 2L squared equals 200, and then divide both sides by 2, and I get L squared equals 100. And then I take the square root of both sides, and I get L equals 10 and a -10, because both of those work, right? -10 squared times, -10 times -10 is 100, so that works. However, this is a problem where I'm working with the lengths, and so the -10 is not something we want to consider. It's still a critical number, but it's for this function. But because we're dealing with real lengths, we don't want to have a negative length. So then L equals 100 is the critical number that I'm going to look at. And it's the only one I'm going to look at. All right. And so we're not done. We found the critical number, but the second derivative test says we need to evaluate the critical number at the second derivative. So remembering that the first derivative is equal to 2 minus 200 L to the -2, and that's coming up here. That's what I'm using right up there. Okay, so now I'm going to use that to take the second derivative. So the derivative of the first derivative, and the derivative of 2 is 0. So I'm going to get -200, bring down the exponent, -2, and then I have L, reduce the exponent by 1, I get -3. So I can write that as 400 over L cubed. And now we want to take the second derivative, evaluate it at my critical number, which was 10. All right, remember, that's my critical number, so I want to put that in here. And look at the second derivative there. So I have 400 over 10 cubed. All right, and I can figure out what that is specifically, what specific number that is, but it really doesn't matter, because what I want to know is whether it's positive or negative, and that is going to be a positive number. So what does that mean? That means I've got a second derivative that's positive, that gives me a smiley face, and at the bottom of that smiley face is my critical number, and so that critical number is a minimum. So that tells me that when L equals 10 meters, that gives us the smallest value, the minimum value, the smallest value. Okay, great. All right, but we're not done because we have to answer the original question. What was the original question? The original problem here, circling in blue, says find the dimensions of a rectangle. So we found one side, the L, but we need to find out the W. Well, remember, we had L times W equals 100, which meant then that W was 100 over L. And that's what we used earlier in the problem. Now that we know what L is, we can solve for W. So W is 100 over 10, which when I reduce that, I get 10 meters. So this is the value for W. So my dimensions of the rectangle that has the area equal to 100, but gives me the smallest possible perimeter. Those dimensions are 10 by 10 meters. And I'll just box that in by red there. That gives me that. Now, what's interesting with this is what type of rectangle that is. That is a square. So the square gives me, of all the rectangles who have a fixed area, the square gives me the one with the smallest perimeter. Let's look at another example. In this one, we have a farmer with 500 feet of fence and wants to enclose a rectangular area and then divide it into 4 pens with fencing parallel to one side of the rectangle. What's the largest possible area of the 4 pens? So in this problem, I think it's very helpful to draw an image of what you're trying to do. So what do we have? We've got this rectangular area here, and we're putting some fencing in here so that we have 4 different pens. So we've got like this pen here, and then we've got this pen here, and we've got another one here, and a 4th one here. All the black area is fence, and the total amount of fence is 500. Now, the farmer wants to make these pens so that the total area is as large as possible. And in this case, we're going to be making them all, we could make them all the same length, it doesn't really matter, but that would make the areas the largest. And now, why would a farmer have this? Maybe they want to put pigs in the red one, they want to put chickens in the blue one, some different animal in the green one, and so forth. So this would be trying to, given us a fixed amount of fence, trying to maximize the amount of possible area for the animals to live in, but they're all separated from each other. All right, so now let's look at this, put in some specific examples of numbers here. If I made this vertical side here 20 feet, then how much fence is used? Well, we've got here, I'll do this in purple. We've got this side, that's 20 feet. We've got this one, that's another 20 feet. This one, that's another 20 feet. This one's another 20 feet. And this one's another 20 feet. So we've got really 5 times 20 feet in there. So that's 100 feet for that purple vertical fencing there. And then on the other side, I'll use red here. At the bottom, we've got this one in red. And what is that length there? That one, if you think about this a little bit, you could figure out that this would have to be 200 feet. And this top one, again, having some more fence there, a horizontal fence, would be 200 feet. So that if I've got 2 times 200 feet, then that's going to give me 400 feet. And so if I add all the vertical fencing with the horizontal fencing here, I'm going to get 500 feet, which is how much we have. And if I had this situation, then what's the total area? The total area would be 200 feet, which is this bottom part, times 20 feet, which is this part here. And that would give me then 4,000 square feet of area. Now, is that the best answer? Well, we don't know. That was just one example. I could try other numbers and I could try and get a different result. And maybe it's better, maybe it's not better. I could keep trying this over and over again, but let's do the math. If we do the math, we can solve this out and get the exact correct answer. So what I'm going to do is I'm going to redraw my diagram. So I have this rectangle. All right, and I've got my 4 pins inside it. And I'm going to call the bottom length X and the side length Y. All right, so this is, again, in doing these problems, I listed those 5 steps I have. This is my first step, which is defining my variables and then and getting an equation. So X is going to be the length of the bottom rectangle, and Y is going to be the width of the rectangle. And now the equation I'm given is that I have 500 feet of fencing. So how is that represented in terms of my X and Y? Well, for the total amount of fencing, I've got 1Y, 2Ys, 3Ys, 4Ys, 5Ys. So the fencing there, the amount of fencing is going to equal 5Y. And then in the blue, how many X's do I have? I have a blue there and a blue there. So it's going to be 2X. And now we said the fencing was 500 feet. So I now have this equation, 5Y plus 2X equals 500. All right, so I've got my variables and I've got an equation that's given to me in the original problem. The second step is, what do we want to minimize or maximize? Well, we want to maximize the area of the rectangle. I want to maximize it because the problem says we want to get the largest possible area of the 4 pins, which would be the maximizing the area of the rectangle. Okay, and what is that? So we're going to say area equals, it's going to be X times Y. All right, so now we've got our variables. We've got an equation that was given to us, and now we have the function that we want to maximize. But that function has 2 variables, X and Y in there. So it's going to be useful to get rid of one of those variables. And how are we going to get rid of it? We're going to use the equation from part 1. So in number 3, we're going to write a function of 1 variable. And I'm going to take what I have here, this 5Y plus 2X equals 500, and solve for 1 variable. It doesn't matter which one I solve for. I'm going to solve for X because I think that one's going to make it a little bit easier, but not a lot, but a little bit easier. So solving for X, I'm going to bring the 5Y to the other side. So I get 2X equals 500 minus 5Y. And then I'm going to divide by 2, and I'm going to get X equal to 250 minus 5/2 Y. All right. And now what am I going to do with that? I'm going to use this, and I'm going to plug and substitute that into my equation for area. And when I do that, so area is X times Y, but X is 250 minus 5/2 Y. And so then I'm going to times it by Y. So what I've done is put this in for X right there. So I can write now my function is going to be in terms of the variable Y, and I'm going to have 250 minus 5/2 Y all times Y, which then I could write as 250Y minus 5/2 Y squared. Okay, so there's my function for area, and it's in terms of 1 variable, which is what we want. So that was part 3. So now part 4. I'm going to take my function. Again, it's a of y equals 250y minus 5/2 y squared. and I am going to do the second derivative test for that function. So I take the derivative. I'm going to get 250 minus, I bring the 2 out front, multiply it by 5/2, I'm going to get 5y to the first power, and I set that equal to 0 to find the critical numbers. All right, if I bring the 5y to the other side, I have 250 equals 5y, divide both sides by 5, and I get 50 equals y. That is my critical number. Only one I have here. And now I want to see whether I want to guarantee that it's a maximum. That's what I'm trying to find. So I'm going to use the second derivative. So what's the second derivative of the area? Well, it's the derivative of the first one. So remember, we're going to use now here in blue, we're going to take the derivative of this, bring it down here. When I take the derivative of that, the 250, the derivative of 250 is 0. The derivative of minus 5y is minus 5, like that, no variables. Well, no matter what x or y, no matter what y value I put in there, that's always going to be negative, right? The second derivative at 50 is still going to be -5, and that's less than 0. So when I have it being less than 0, negative, I have 2 negative signs, which is like this. And because I have a critical number, then at the top of that is my maximum. So this tells me that at y equals 50, okay, we have a maximum. And that in terms of this problem, that means y equals 50 is going to give me my maximum area. Now, some of you may be saying, well, because the second derivative is always -5, I could put in other numbers and get something negative, and that would give me a maximum too. You would get a negative number, but it doesn't give you a maximum because you have to put a critical number in there. And we can't just put any number in there. We only if we put in a critical number do we get a maximum. So it is true that the second derivative, no matter what number you put in for y, you'll get a negative, but that doesn't guarantee it's a maximum. It only guarantees that it's going to be concave down at that point, right? You have to put in a critical number. Okay, so last step is to answer the question. What was the original question we had? Well, going back here, circling this, the question is, what's the largest possible area of the 4 pens? All right, we figured out y. We have y equals 50, and that's going to be in feet. So what is x? All right, well, we're going to go back to here. Remember that we had this equation that it was 5y plus 2x equals 500, and we solved for x. X equals then 250 minus 5/2 y. All right, so we're going to use that to find x. So x is going to equal 250 minus 5/2, and now we'll put in the y value. The y value was 50. All right, coming from here, we're substituting that in there. And that gives us then that x is 250. When I multiply 5 times 50 and divide by 2, I'm going to get 125. So x is going to equal 125 feet right here. That's my x. Now I'm not done, because what am I supposed to find? We're supposed to find the max area. Well, and the area, what was area? It was x times y. So now I can put these in. I have 125 for x, 50 for y. And when I multiply those together, then I'm going to get 6,250 square feet. And that's going to be my final answer, the maximum area of the 4 pens put together. Let's look at a third example. Here we're supposed to find the point on the line y equals 3x minus 1 that's closest to the point 2, 0. So let's draw a diagram, a picture, to help us understand what's happening here. All right, so I'm going to put in some point values here. This is my x-axis. This is my y-axis here. I've got the graph y, or the line y equals 3x minus 1. So that means I have the y-intercept at -1. It goes up 3. Rise over run is 3. So 1, 2, 3 over 1. So the graph of that line looks something like this. Okay. And I have the point 2, 0. That's this point right here, 2, 0. And now I want to find, if I were to draw a line here, I want to find the shortest distance for this line that connects the red dot here to, let's see, that didn't work. It connects the red dot to the blue line. All right, so let's put, I'm going to put another dot here on the blue line, and I don't know exactly where that dot is. I can, that orange, and what color is it? Orange or yellow, gold? I never know quite what this is. So on that orange dot, if it moves up and down, the distance will change. And I want to find where that is, the X and Y value, where that will make the green line the shortest. So I'm going to call the orange one X, Y. All right, so here's my setup, and let's work through the steps that we have here. So we're gonna use the point X, Y to be the point on the line y equals 3x minus 1 that is closest to the point 2, 0. We don't know what it is, but that's what we're trying to find. All right. Okay, that's about the information I need. Now I need to find a function that would represent what I'm trying to minimize. This time I'm trying to find the shortest distance, so I'm trying to minimize the distance. Well, what is the formula for the distance between 2 points? So distance between the points X, Y and 2, 0 is given by this function here. It's X minus 2 quantity squared plus Y minus 0 quantity squared, and I take the square root of that. All right, that actually is a variation of Pythagorean's theorem. So we're taking the differences of the Y's, the differences of the X's, squaring it, and adding to that the differences of the Y's and squaring it, and then we take the square root of it, and that will give me my distance. Okay, so that's the distance formula. So great, we've got now our variables X and Y. We know that Y equals 3x minus 1. We've got the point 2, 0, and we've got this distance formula. So next we need to rewrite this function d so it has one variable. So let's see, what am I going to get? What can I do? Well, notice that if we use the original, this y equals 3x minus 1, we could substitute that into the y there, and that would be really nice, because that y minus 0 is just going to, the 0 doesn't affect it any because it's just 0. So we're going to use that. We're going to do x minus 2 squared plus, we have this y squared here. That's what we get. That's just doing this right here. But now we're going to add what y is. So we're going to say this is x minus 2 squared plus, and instead of putting y in there, we're going to put 3x minus 1 squared, like that. And again, where does that come from? That's this blue equation, and we're putting that in for y there. Okay, now I can work on this a little bit. So my function is going to be d of x, because x is my variable. I can square this, so let's just remember x minus 2 quantity squared means x minus 2 times x minus 2. So if I FOIL that out, I get x squared minus 2x plus 4. So I get x squared minus 4x plus 4. And some of you I know could do this in your head. So please just bear with me as I write out all the gory details here. But that's what I get. This is equal to that part. Okay, and then I have 3x minus 1 squared. So that's 3x minus 1 times 3x minus 1. And when I multiply that all together and FOIL it out, I'm going to get 9x squared minus 3x plus 1. And that's going to be 9x squared minus 6x plus 1. And so I'm going to get a 9x squared minus 6x plus 1 here. And that is for, using a different color here, that's this part here. And then I got, after I add those together, I've got the square root of all that. Okay. Next, then we've got this d of x. We're going to take what we have here, bring it down here, and we want to combine like terms. So I've got this x squared and this 9x squared. That's going to be 10x squared. Oops, let me do that in black. That's 10x squared. And then I've got this negative 4x and this negative 6x. So that's going to be negative 10x. And I've got plus 4 and plus 1. That's going to be plus 5. And it's all under the square root. Okay, so there's my function. We've got my function. And now we can do the second derivative test on it. So now we're at step 4. Function d of x, which equals the square root of x squared minus 10x plus 5. All right, we're going to take the derivative of that. Now I'm going to stop for this for a second, and I want to show you something. All right, let's take the derivative of this. So I'm going to write this as 10x squared minus 10x plus 5 to the 1/2 power. If I take the derivative of that by the chain rule, I bring the 1/2 out front, write down what I have inside the parentheses, reduce that by the exponent by 1, so I'm going to get negative 1/2, and then I take the derivative of what's inside the parentheses. That's the chain rule here. Okay, so if I rewrite that, I get the derivative of 10x squared minus 10x plus 5 over 2 times the square root of 10x squared minus 10x plus 5. Now, because we're finding the critical number, we want to set this equal to 0. When that happens, what becomes important? Well, what becomes important is what's in the numerator. The denominator can never equal 0, and so it does not affect the value of this derivative if we're setting it equal to 0. So the critical numbers just matter what's in the numerator, and that is this derivative here. Well, wait a minute. This is like amazing because we don't have to take the derivative of the square root. We only need to take the derivative of what's inside it. So what is important in terms of finding the critical number is to find the derivative of this, what's inside the square root, and setting that equal to 0. All right, that is going to make our life a lot easier when we do these problems. So we're going to define this function, capital D, just to be what's inside the square root. All right, and now if we find the critical numbers for that capital D, we're going to get the same critical numbers for the small d, which was the square root of all this. All right, so let me re-say all this. All right, if we take the small d, which is this one with the square root here that I'm circling in purple, if we do that and we go through this process here, what do we end up with? We end up with this result here. And what is important when we're finding the critical number? The important part is that the numerator here equals 0. Well, what is that numerator? It's just the derivative of what's inside the square root. All right, so we don't have to take the derivative of the small d, we can just take the derivative of what's inside the small d, and that is what we've written here by this capital D. Now you may say, well, I just want to take the derivative of the small d with the square root. That's fine. It's not so hard when you take the first derivative. But to do the second derivative test, we have to take the second derivative of that, and that gets a really kind of complicated. So it's just easier to consider the capital D without the square root, just what's underneath the square root. All right, so that's what we're going to do. We're going to let capital D be what's under the square root, and now we're going to do the second derivative test to that. So capital D is then going to be, the derivative of capital D is going to be 20x minus 10, and that's equal to 0 because we're trying to find the critical number. If I solve for x, so I've got 20x minus 10 equals 0, add 10 to both sides, divide by 20, I get x equals a half. We found the critical number. All right. If you do it by what's circled in the purple there, with the small little d, you're going to get the exact same critical number. All right. Here's though where it's a lot easier, because now if I do the second derivative here, I'm going to get the derivative of what we have here in green. And when I do that, I get 20. Well, I don't have any x's left. So that's always greater than 0. So that means I have plus plus, smiley face, and at the bottom of that smiley face, because I have a critical number, it is a minimum. So that means at the critical number, x equals a half, we have a minimum. So at x equals a half, we get the shortest distance, okay? Because that represents what we're trying to find, the minimum there. All right, let me again just point out that if you didn't like using the capital D and you decided to go with the little d that we have up here, I'm going to again circle that this time in a dark green. Then I got this first derivative here, boxed in this dark green. Now I have to take the derivative of that a second. I take that again to get the second derivative, and that becomes really, really, really complicated. Why make it complicated when we don't have to worry about it? So that's why we use the capital D there. All right. So we've now done part 4. We are left with doing part 5, and that is answering our question. And the question, again, going to the original problem here, I'm going to mark it in blue, is find the point on the line y equals 3x minus 1 that's closest to the point 2, 0. All right. Well, we found the x value. We had x equals a half. So what is y? Well, remember, y was equal to 3x minus 1. So now we're going to put in the x value there, a half. And so we get 3 halves minus 1, which gives us a half. So y is equal to a half. And so my point, x comma y, is 1/2 comma 1/2. And that is the shortest, that is the point on the original curve that is shortest, gives us the shortest distance to the point 2, 0. And let's see, does that kind of make sense here? If we go back to our original drawing here, remember the orange point here, we just figured out that that was 1/2, 1/2, and that kind of looks like what we have in our graph here. All right, so it makes sense. All right, let's do one final example here. In this problem, it says we've got the top and bottom margins of a poster are each 2 centimeters, and the side margins are each 1 centimeter. If the area of the printed material on the poster is fixed at 200 square centimeters, find the dimensions of the poster with the smallest area. All right, so again, let's draw a diagram to help us see and visualize what's happening here. So I've got this poster, and inside we've got some printed area. So this is the printed area inside there. We'll say printed area. And we know that we have a margin here that's 2 centimeters and 2 centimeters here, and 1 centimeter here, and 1 centimeter here. And we also know that the the area of the printed material is fixed at 200 centimeters squared, and we're supposed to find the dimensions of the poster with the smallest area. That's the total poster, okay? So we're gonna let X, I'm gonna write this in terms here, we're gonna let X be this length and Y be this length. So X equals the length of printed rectangle, and Y is going to equal the width of the printed rectangle. All right, so we know then that X times Y is 200. Okay, so this is then part one. We've defined our variables, and we've got an equation here using the material that's given us, and that is X times Y equals 200. All right, so now we need to, the next step is to, what are we trying to minimize or maximize? We want to minimize the total area of the poster. So the total area of the poster is not the printed area, but it's going to be this big poster, this big rectangle. So I'm going to have this area, this length, and this length. So what's the bottom length? Well, it's going to be X plus 2, and the vertical length there is going to be Y plus 4. How did we get that? Well, again, remember, this length is X, and then I've got this 1 and this 1 here. So I'm going to get X plus 2, because I'm going to have X plus 1 plus 1. And in the other direction, we've got this length here, which is Y. So we've got 2 plus Y plus 2. So that's going to give me the Y plus 4. So we want to minimize this area, which we're going to call A, and that's going to be minimize X plus 2 times Y plus 4, right? That's what we're trying to minimize. Okay. So now I need to get a function, I need to get my function A in terms of one variable. Well, we're going to use the fact that X times Y is 200. We're going to solve for one of my variables. Let's solve for Y. So Y is going to equal 200 over X, dividing both sides by X. And then remember, A was X plus 2 times Y plus 4. So now we're going to take the Y equaling that, and we're going to substitute it in here, and I'm going to get a function in terms of my one variable X, and it's going to be X plus 2 times 200 over X plus 4. All right, because I've again substituted in for my Y here, substituted in there, and simplified that. Let's multiply this all out. So I'm going to have to FOIL. So when I do that, I've got this times that. That's going to give me X times 200 over X. All right, and then I've got X times 4, so I'm going to get 4X. And then I've got a 2 times that, so I'm going to get 2 times 200 over X. And then last, I've got 2 times 4. That's going to give me 8. So I can rewrite this as A, the X equals, well, the X here times the 200 over X is going to cancel out. I'm going to get 200. And then I have 4X. And then the 2 times the 200 is going to give me 400 over X. And then I have plus 8. All right, so now we're going to do second derivative test. We want to take the derivative of this. So when I take the derivative, I get the derivative of 200, that's 0. Derivative of 4X is going to be 4. Then I have the derivative of 400 over X. Well, remember, we could write this as 400 X to the negative 1. So when I take the derivative of that, I bring the negative 1 out front, and I'm going to get 400 times negative 1 X to, and I reduce the exponent by 1, so I'm going to get minus 1. So I'm going to get minus 2 there. And then finally, I have the derivative of 8, and that's going to be 0. So my derivative here is going to be 4 minus 400 X to the negative 2, which I can write as 4 minus 400 over X squared. And now we want the derivative, we want to find the critical numbers, so we want to set this equal to 0. So I've got 4 minus 400 over x squared equal to 0. All right, bringing the 400 over x squared to the other side, I get 4 equals 400 over x squared. And now multiplying both sides by x squared, that will give me then 4x squared equals 400. Dividing by 4, I get x squared equals 100. And taking the square root of both sides, I get x equals 10 or negative 10. But as we saw earlier, we don't want negative values. So even though negative 10 is a critical number for this function a, we are only concerned about x equaling 10. All right, so now we need to do the second derivative test. So I take the second derivative of my function. Remember that my original function, when I took the derivative, I got this. Okay, or even better, let's do this one here. All right, so the second derivative now, I'm going to, let me just redo this here. I'm going to have the first derivative here was 4 minus 400 x to the negative 2. So the second derivative, I'm going to take the derivative of that. When I do that, I'm going to get negative 400 times negative 2, and I get x to the negative 3. So that's going to be then 800 x to the negative 3, or I'm going to get 800 over x cubed. All right, so when we look at the second derivative at 10, that's going to be 800 over 10 cubed. And again, it doesn't matter what that is because that's going to be positive. And so positive, positive gives me happy face, smiley face. And at the bottom, I then have a minimum for my critical number. So that tells me then that x equals 10 gives the smallest area, which is what we wanted, smallest area of the poster. All right, and so then last thing is to answer the question. And the original question, going back here, the original question is find the dimensions of the poster with the smallest area. So we figured out what x is. So now we need to figure out what y is. So y is, going back to the original equation, we had that y was 200 over x. All right, let's just check that here. Yep, that's what we have here in green. Y equals 200 over x. So we brought that down here. And we know that x was 10. X is 10. So y equals 200 over 10, which is 20. So my dimensions are going to be x is 10 centimeters and y equals 20 centimeters. And that gives me the poster with the smallest area. All right, hope that helps you. Have a great day.